So hey guys, welcome to the channel Learning Competitive Programming with CodeChef. So if you want to learn data structures and algorithms and master competitive programming, this is the one-stop destination for you. Every week we will be posting several videos on CodeChef problems as well as various programming paradigms. So before moving forward, one small request for you. If you are new to the channel, then please do subscribe the channel and turn on the bell notification. Okay, so the problem that we are taking today from the August Cook Off is K-Foldable String with problem code K-Fold. The difficulty level of the problem is easy and the prerequisites of the problem is none. Okay, so let's look at the problem statement. The link to the problem statement is in the description also, so you can check it from there. So I'll quickly summarize you what the problem says. Basically, we have been given a binary string S with length n and an integer k. So k is the divisor of n. A string is said to be k-folded if it can be changed to a string with length k by repeating the following process. So a string is said to be k-folded if a string can be changed to a length k string by repeating the following process without any collisions. So we'll define the collisions in this statements also. Alright. So first what we will do, we'll select the prefix of the current string s of length 2k. So we'll take a prefix of length 2k from the string. And there will always be a prefix because the length of the string s is greater than k, right? So there is always a prefix. The prefix will always exist. All right. And for each I, check if 2k minus I plus 1th character of s is not equal to the ith character of s. If they are not equal, then the collisions exist and the process is invalid. So we'll check whether the ith character matches with 2k minus I plus 1th character. So if it does not match, then the collision will exist and will not further move the process because it will be invalid. Right. Now for each I, where I is between 1 and k both inclusive, replace 2k minus I plus 1th character of s with the ith character. So we need to replace that particular 2k minus I plus 1th character with the ith character. And right, so what we'll do, we'll remove the prefix of length k from it. So in the first step, what we will do, we'll remove the prefix of length k from it. So first what we have done, we have selected a prefix of length 2k. Then what we will do, we'll match the ith element with 2k minus I plus 1th element. If it does not match, then the collision would exist and then the process is invalid. Otherwise, what we'll do, we'll replace the ith character with 2k minus I plus 1th character. And then what we'll do, we'll remove the prefix of length k from that particular string s. Alright. So what we need to do, we have been provided with a string, and to make it k-foldable, we need to rearrange the string such that this process happens, and at last what we are left with, a string of length k. Okay, so until we are not done with the string of length k, we'll continue with the process. And if there is a multiple answers, then what we need to do, we need to print the lexicographically smallest one. All right, so we need to print the lexicographically smallest one if there are multiple answers existable, right? So what are the inputs and the output? The first line will contain a single integer t, which denotes the number of test cases, and then we have two integer, that is n and k. N is the length of the string, and k that we are provided with the k-foldable string, the value of k we have been given. All right, the second line consists of the string which is of length n. So these are the inputs, right? The output is that if it is possible to rearrange the string according to the given condition mentioned in the problem, then what we need to do, we need to print the lexicographically smallest string. Otherwise, what we need to do, we need to print impossible. Right? So if the string is not possible according to the given conditions described in the problem statement, we'll print impossible. Otherwise, what we'll do, we'll print the lexicographically smallest string. So what are the constraints of the problem? Test cases ranges from 1 to 100, and k and n ranges from 1 to 10 to the power 3, and is divisible by k as mentioned in the question. And s contains only two characters, that is binary characters 0 and 1. So this is the whole description about the problem statements. Let's look at the example. So if we have two test cases, the length of the string is 8 and the value of k is 2. So we have been given this string. So can we rearrange the string? Yes, we can rearrange. The possible string must be this. And how the things are working, let's see in the explanation of the example. That first what we'll do, we'll select a prefix of length 2k, that is 2 into 2, that is 4. So first we'll select this prefix. We have rearranged the string into this, so we'll select this prefix. As we can see, the ith character matches with 2k minus I plus 1th character. So what we'll do, we'll remove the prefix of length k. So we'll remove 0 1 from here. So after first step, what we'll do, we'll remove 0 1 and the leftover string will be this 1 0 0 1 1 0. Similarly, again we'll select the length prefix of length 2k, that is 4, and then we'll match ith character with 2k minus I plus 1th character, and then also we'll see that everything is matched, so we'll remove the prefix of length k, that is 1 0. Similar process here also, we'll see that it matches or not with 2k minus I. 2k minus I plus 1th character matches with the ith character, and then what we'll do, we'll remove the prefix of length k, that is 0 and 1, and at last what we are left with a string of length k. That means the whole process is complete, the conditions are working, and this is the lexicographically smallest string, so we'll print this string. So in the second case, we are not able to find any string with that particular conditions fulfilled, so what we'll do, we'll print impossible. So this is the whole description about the problem statement with the example test cases and the constraints. Okay, so the agenda for today is, the first step will be, we'll understand the concept of mirroring. After that, we'll move towards the logic of the problem. The logic of the problem is again divided into two parts. The first part is whether it is possible or impossible to make the string. If it is possible to make the string, then we'll come to the second part, that is which string is lexicographically smallest. And after that, what we will do, we'll try to implement our logic into the code written in C++. So this will be the agenda or the table of contents for today. Okay, so before moving towards the solution, let us try to understand a small concept of mirroring, right? So what we are trying to do here is, we are trying to form the mirror images, right? So let us suppose that we have been given k equals to 3 and the string is 0 1 0 0 1 0. So this is the string that we have given, and we need to find that if the certain condition holds true, or it is impossible to make it k-folded, right? So the condition that we have been given is the ith character must match with 2k minus I plus 1th character, right? So let's take for I equals to 1. So I ranges from 1 to k, right? So for I equals to 1, the character is this one, that is this one, for I equals to 1, and it must match with the 2k minus I plus 1th character, that is 2k means 6, 6 minus 1 plus 1, that is the 6th character in the string. So the 6th character in the string is this one, so it matches with it. Similarly, we'll proceed for I equals to 2, that is for this one, it must match with 2k minus I plus 1th character, that is 5th character, right? So it matches with the 5th character. Similarly, for I equals to 3, that is this character, it must match with the 4th character. So we have seen all the binary numbers from I equals to 1 to I equals to 3, and it matches with 2k minus I plus 1th character. So we can see a pattern here that this is building a mirror image over this k equals to 3 index, right? So all the binary digits before k equals to 3 is forming a mirror image after for all the digits after k equals to 3. We can see a 0 1 0 is forming a mirror image over here, right? Let us try to take some other example, right? So let us take a string of like this 0 1 1 0, and if k equals to 2, we can see that there is a mirror image formed here, right? If k is equals to 2, then there is a mirror image formed here, and it is a k-folded example, right? I am talking about k-folded examples. So we can see that the first character matches with the 4th character, the second character matches with the 3rd character. So this concept of mirroring is used in the question. So let's see how we can use this concept in developing the solution of the problem. Okay, so we have seen the concept of mirroring, and now let's try out the logic of the problem. So let us try to build the intuition with the help of some examples. So suppose we have k equals to 3 and we have this string. The length of the string is 9. So let's start step by step according to the question that what we need to apply on this particular problem. So if k equals to 3, then what we will do, first we'll select the prefix of length of 2k, that is 6, right? So we have selected a prefix of length 2k. Now we can see in this particular prefix we need to match the ith value with 2k minus I plus 1th value, right? So we need to match these values. So as we have seen in the concept of mirroring, it will form a mirror image over this particular point. So for every particular segment of k equals to 3, it will form a mirror image over the next segment. So let us try once more. let us move towards this particular part. So if we have seen this particular segment and we have seen in the earlier part that it will form a mirror image, so what we will do in the next part, we'll replace I value with 2k minus I plus 1th value, and then we'll remove the prefix of length k. So what we'll do, we'll remove the prefix of length k, and then we'll see the next part. So in the next part also we can see that it is forming a mirror image over this particular length, that is k equals to 3. So it is forming a mirror image from this part of length k equals to 3 to the next part, right? So again what we'll do, we'll select the prefix of length k and then we'll remove it after replacing the values, right? So we are left over with this part, and hence we are sure that the string is k-folded. All right, so the first thing that is coming into our mind is that how many segments are there. So first of all, I am matching these two segments of mirror images, of the concept of mirror images, and then I am checking these two segments, right, for the concept of mirroring, as we have seen in the conceptual part of mirroring. So in all I have 3 segments here. So how we can calculate the number of segments, that is the total length of this particular string divided by k, that is k equals to 3. That gives us the number of segments. And for each segment, what we need to check? We need to check that the consecutive segments are mirror images or not. So for the whole string, we'll check this, that whether the consecutive segments are mirror images or not. And if this situation holds true for the whole string, then our answer is yes, that it is possible. Otherwise, the answer is impossible. And if it is possible, then we'll see that how we can permute the lexicographically smallest string, right? So we have seen that the segments are 3 here, that is 9 divided by 3, that is equal to 3. So the question arises that how we can check that if a string can be converted such that the consecutive segments are mirror images of each other. So this is the important question that arises in our mind. So let us look at the example 1. So these are 2 consecutive segments. What is the similarity that we can find in these 2 consecutive segments? That is, the number of ones here are equal here. That is, there are 2 number of ones, and here also there are 2 number of ones. There is only a single 0 here, and here also there is a single 0. That means the number of ones in the segments, in the consecutive segments, must be equal, as well as the number of 0 in the consecutive segment must be equal. So the 2 important observations that we can derive from the example is that the number of zeros in the consecutive segments are equal, as well as the number of ones in the consecutive segments are equal. So here also we can see that the number of zeros, that is only 1 0 is there, so these both are equal, as well as the number of ones are also equal, that is 2 ones here and 2 ones here. Alright, so in the consecutive segments, if we need to check the condition for the mirror images, that means that the number of ones and the number of zeros must be equal. Alright, let's look at the bigger picture. The bigger picture for the whole string, right? So if we look at the whole string, that means this particular segment is the mirror image of this segment, right? And this particular segment, the third segment, is the mirror image of the second segment, right? So if there is 1 0 here, that means that there must be 1 0 here, because these 2 are mirror images. But then also these 2 also are mirror images. So if there is 1 0 here, then there must be 1 0 here also, right? And same condition is for 1. So if there are 2 ones here, then there must be 2 ones here, and there must be 2 ones here as well, because this is the mirror image of this segment, that is segment 2 is the mirror image of the first segment, and segment 3 is the mirror image of second segment, right? So for each of the segment, there must be equal zeros and equal 1. So the bigger picture of the problem is that the number of zeros in all the segments must be equal, as well as the number of ones in all the segments must be equal. So this is the bigger picture of the problem. First, what we have done, we have broken down the problem for the consecutive segments. And when we find the similarities in the consecutive segments, we have boiled down our conversation, our problem thinking, to a certain point that the number of zeros and the number of ones in all the segments must be equal, right? So this is the important observation. So what happens if the number of zeros and number of ones are not equal? So let us suppose that we have converted this 1 to 0. So as we can see, the mirroring concept in this particular two segments, the two consecutive segments, fails down, and hence we cannot form a particular solution towards it. Hence our answer would be impossible here. All right. So how can we divide number of zeros and number of 1 equally in all segments? This is the question, that are we able to divide it or not, right? So how can we do this? So let us take this example forward, that we have this string and we want to divide number of zeros and number of ones equally in all segments, right? Equally in all segments, and check whether we are able to divide it equally or not. First thing is whether we are able to equally divide it in all the segments or not. So this is the possible pseudocode that we can possibly think of. That is, what we'll do, we'll count the number of zeros and count the number of ones in the whole string, and then we'll divide it by the total number of segments, right? So if the remainder is 0, that means that we are actually able to divide these particular numbers to all the segments equally. So let us suppose that we have total number of zeros as 9 and we have 3 segments. So what are the possible cases? We can divide total number of zeros to each segment, that is, we can give 3 zeros to each segment. And if we have 10 zeros and we have 3 segments, then we cannot divide number of zeros to each segment equally, because it will leave one remainder, that is 1 zero is left. All right, so if we put 3 zeros in each segment, then also 1 zero will be left. So where we will put that 0? So to divide equally total number of zeros and total number of ones, we need to check that if count of 0, that this count of 0 is storing total number of zeros. So if count of 0 modulo total segments, that is these segments, will give remainder 0, and the count of 1, for 1 also we'll check that if count of 1 modulo total segments will give the remainder 0, then that means that the answer is possible. Otherwise the answer is impossible. So the first condition of finding whether we can make the string or not is completed here. So if the total number of zeros, the count of total number of 0 modulo total segments equals to 0, and the count of total number of 1 modulo total segments equals to 0, that means the answer is possible, otherwise the answer is impossible. So this is the first possible condition. And now let's look at the second part of this problem. So the second part of the problem states that how we can find the logic of a lexicographically smallest string. So the first thing is, we have only two numbers, that is 0 and 1. So if we look at the condition, that first we have found out that we can make the string, right? So in the first part of this video, we have found out that we can make the string possible. But now let us try to understand that how we can make it lexicographically smallest. So there are only two possible conditions. The first condition is that if we put number of zeros that we have in a particular segment first and number of ones afterwards, right? So if we put number of zeros first and then number of ones, then in the mirror image it will form number of ones first, and after that it will get number of zeros. And the second possible case is if we put number of ones first and then number of zeros, right? So in the mirroring part, that is the second part of this particular case, it will have number of zeros first and then number of ones. All right, so we can see in the first case that this particular string is lexicographically smaller than this string because it has the number of zeros first, right, and it has number of ones first. So this particular string is lexicographically smallest. So this is very easy concept to understand, that for each segment what we will do, we'll first print the number of zeros that are required in this segment, and then afterwards we'll print number of ones. And the second segment, that is the consecutive segment, must have the number of ones first and then number of zeros, because it is a mirror image of the first segment. All right, so this is easy to understand. So the first case is lexicographically smaller. All right, so as we can see in this particular slide, that for all the even segments, why I am choosing even segment, because the first segment will be even, because we are taking the index 0. So the first segment will be even. So for all the even segments, we'll print first all the zeros, and then afterward we'll print all the ones. And for all the odd segments, what we will do, we'll print the number of ones first and then the number of zeros, right? So let us take this string. Let us take an example of this string. So if we have this string, then this is the even segment because indexing is 0. So what we'll do, first we'll print the number of zeros and then we'll print the number of ones. And this is the odd segment because the indexing is 1. So we'll print the number of ones first and then the number of zeros. So this will lead us to the lexicographically smallest string. And now let us look at the code of the solution. Okay, so now let us understand this code which is written in C++. So first what I am doing is I am inputting all the test cases, right? And for each test case what I am doing is I am inputting two values, that is n and k, as given in the question. And then I am inputting a string that is stored in S. Now the second part of the string is, as we have discussed in the approach of this problem, that what we need to do, we need to take a count of number of zeros and number of ones in the string. So for I equals to 0, I less than string dot length, what I am doing is, if this value of the string is 0, then I am incrementing count 0, that is storing the number of zeros in the string. And else what I'll do, I'll increment count 1, that will store the number of ones in the string. So I think this code is pretty easy to understand. This is the main logic of this particular problem. So as we have seen that we have to calculate the number of segments of that string. So what was the number of segments? That is the total length of the string divided by k. So what I am doing is I am making a variable naming number of segments, and what we'll do, we'll divide n with k. So it will give us the number of segments. What was the condition in which we are doing the whole process? So first what we'll do, we'll check that whether we can make the string or not. So what was the condition? If the total number of zeros modulo the number of segments are giving the remainder 0, right? And the total number of 1 mod number of segments that we have is giving the remainder 0, that means we can enter in the condition. That means we can process the string. Otherwise it is impossible to process the string. So if these both conditions hold true, that means we can process the string. So we will process the string here. Otherwise what we will do, we will output impossible. Alright, so what was the process of making a lexicographically smallest string? That is, for I equals to 0 till I is the number of segments. So for each segments what we are trying to do, so if the segment is even, then what we will do, we'll print the number of zeros first and then the number of ones. And if the segment is odd, then what we will do, we'll print the number of ones first and then the number of zeros. So what we are doing here, we are checking first that if the segment is even. So if I modulo 2 equals 0, that means it is even. If the value of I is even, then what I am doing is I am printing 0 first for all the values. What I am doing here in this particular condition is that for each particular segment, how many zeros I need to print. Suppose that we have 3 segments and we have 9 zeros. So how many zeros I will print each segment? That is 9 divided by 3. That means 3 zeros in each segment. I will print 3 zeros. So that is what I am doing here, right? So I am calculating that how many number of zeros that I need to print in this segment, and then I am printing these zeros. And afterward what I will do, I will check that how many number of ones I need to print in this segment, and then I will print those 1. So first I will print 0, then I will print 1. And for all the odd segment, what I will do, I will use the same logic of printing ones and zeros, and first I will print 1 and then I will print 0. So one more thing you can do here is, you can outside make a string and then first append all the zeros that for each segment require these number of times zeros and these number of times ones, and store it, and then reverse it because we are forming the mirror image, and then reverse it, and then for each even segment print that particular string, and for each odd segment print the reversed string. So this is the alternative approach that you can use, right? So the logic is same, and if this condition does not hold true, then we will print impossible, that we have discussed earlier, right? So this is the whole code in C++ language that we can use for this particular problem. The time complexity of this problem will be big O of n. Why? Because we are running a loop over the length of the string, right? So we are taking each segment and calculating and processing stuff for each segment. And for each segment, what we are trying to do, we are trying to print the number of zeros as well as number of ones. As well as in the earlier for loop, what we are trying to calculate, we are trying to calculate the number of zeros and ones for the length of the string. So the overall time complexity of the problem will be big O of n. Okay, so let's try to submit the code in C++. So we'll paste the code. and then click submit. So the problem is running. And we get the correct answer. The perfection sign AC.